My name is Yiming, and right now I'm a third-year PhD student, supervised by Serge Galas. And today I'm going to talk about our recent work about the predictive distribution of deep Gaussian process gradients and its application in sequential design. So I will firstly give a motivation and some introduction about the problem, and then I will briefly discuss how could we like derive the distribution of the gradient of a GP, linked GP, and the deep Gaussian process, and then I will go through about our newly proposed method in sequential design and show some numerical results. So, firstly, like Gaussian process emulator is used to reduce the computational complexity of modern computer models because in modern society, lots of physical problem can be studied with scientific computing, but this code is very computational intensive and which could not be affordable for doing like intensive computation in some tasks like uncertainty quantification and optimal design. Yeah. Oh, sorry, I have so this. Yeah, but the one important assumption of the Gaussian process is their stationarity, which means they can only approximate the functions with very smoothly without any sharp changes or even discontinuities in the model output surface. But however, such changes widely exist in scientific problems. For example, like the left figure shows a phase transition of water ice from the ice to the water, and the middle one shows the transition of fluid from the very stationary laminate flow to the turbulent flow, and the right figure shows the switch behavior in superconductivity about the temperature. And all such kind of phenomena systematically studied within a subject called the bifurcation theory, which is sub-subject of the dynamical system. So in this work, we consider localization of such sharp changes with a tool for the purpose. One is about the physical findings, because identifying such variations hold importance as they can result in many significant implications of the investigative system and help us better understand the physical system. And the second purpose is like such kind of sharp changes will lead to very uncontrollable error of our approximator. Yeah, and this is a very easy figure to show like such sharp variations degrade our performance of our approximator. Um, yeah, and actually in the approximation theory, the error, the way we control the approximate error comes from two terms. One is how you spread the domain and the space, which means uh, how many samples you have, and we call it a covering number. It describe how well you cover the domain of interest. And the second thing is about our assumption of the underlying function. So we usually assume it has a very good conditions, very good continuity, like Holder continuity or Lipschitz continuity. But for this case, the local behavior was very tricky, and it will lead to your error out of control. Uh, yeah, and from now I will like briefly introduce the Gaussian process. I think most of the guys should will familiar about the Gaussian process in our department. So suppose we have endpoints of the d-dimensional inputs and a corresponding the scalar valued outputs. So the Gaussian process just assume like the output given your input follows a multivariate normal distribution and um, with a mu and a sigma, and the sigma the sigma is covariance matrices, where the correlation describes the kernel function k with one nugget term, which modeling the inherent noise or measurement noise in the system. And the GP emulator has an analytical mean and variance, which give in this way. And um, when we only considering the mean values, it's just the simple kernel ridge regression. Then I will talk about the linked GP, which is a very kind of narrow application of the GP, which emulates the feed-forward networks of computer models, which means like we have lots of computer models coupled together. The output of the last one will be the input of the next one. So we can build a GP emulator for each of the computer models, and we can couple them together. And in previous works, these researchers shows that given certain kernel functions, we can derive an analytical approximation of the global output. So here we actually consider we can observe like a p-dimensional intermediate output, and then this intermediate output will be the input for the final output model and give our corresponding global outputs. And this figure shows hierarchy of the GPs that represent a feed-forward system of two computer models, where the green one with the first layer and the red one with the next layer. Yes, and during the inference, the posterior distribution of linked GP will, as I just said before, is no more analytical tractable. So the hardest part is we need to marginalize out this intermediate outputs. This is very tricky, but given certain conditions, we can analytically solve the marginal integral. For example, actually the kernel should belongs to the exponential family, like commonly used the RBF kernel, the Gaussian kernel, or the Martin family kernel. Yeah, and I don't want to go through the derivation of the formula, but we know that we can compute it analytically with a Gaussian approximation, the mean and the variance to approximate the predictive posterior of the linked GP. Now the deep Gaussian is very similar to the linked GP if we treat the intermediate output is unobservable, we don't know, or is hidden. From this idea, because we can solve the global integral, we can solve the global likelihood. So we can express the condition, the posterior of the intermediate output variable W by the Bayesian rule, and all these two terms in equation 3 of the right-hand side are Gaussian distribution. So this enables many statistical approaches to sample the unobservable intermediate output W from the posterior distribution. So in this framework, we use the stochastic expectation maximization to alternatively impute the unknown W and updating each GP parameters with the following step iteratively. So in each inner loop, we perform imputation step by fixing the parameters of each GP and the global output and input. We can sample the latent variables W from the distribution. And then once we got the samples, we can plug it back to maximize the likelihood for with respect to the each GP parameters. Yeah, and because these sampling approaches, so we also need to account the uncertainty of such kind of imputations. So we construct n-linked GPs by the set of imputed intermediate variable W. So the approximate posterior predictive mean and variance can be obtained in a Monte Carlo way, which is an ensemble expression to count the uncertainties of the sampling. Right, and next we think about the gradient distribution of GP. Well, a key property of Gaussian process is that any linear transformation of the Gaussian process remains a Gaussian process, and the differential operator nabla acts linearly on these functions. So, and the gradient can be obtained by the inner product of the differential operator and the functions. So the predictive posterior distribution of gradients has a Gaussian distribution with the mean and the covariance matrices expressed in this way. And the nabla, sorry, I missed an expression here. And there it should be equal to nabla R times the R minus times Y. And we only need to differentiate about the feature columns about the X star. Yeah. And then we can think about how to extend the posterior distribution on the gradients of the linked GP emulator. The mean part will be easy to handle because the expectation and the gradient are both linears, and our expectation is taken with respect to the variable y. So we can switch the expectation and the gradient operator to directly compute the expectation of the linked GP at the new position X star, which is, if we recall the formula to compute the mean of linked GP, what we do is just differentiate about the columns X star. And the tricky part is about the variance of the gradient estimation, because the variance indeed is a nonlinear operation. And the variance of the gradient is given by, like, you can see like nabla tensor nabla transpose, which just looks like the Hessian matrices of the Hessian operation of the variance, but this does not extend directly to the linked GPs. So to handle the nonlinear uncertainty propagation across the layers, we use one method called the delta method, which approximates the variance using a Taylor expansion around the mean value. So, actually, we express the gradient of the global output variable in this way, and we can differentiate through the chain rule. But remember, the X star is the intermediate random variable. So actually, that should be this term should be a random variable. So yeah. Yeah, sorry. That should be a random variable, but that increase the difficulties of our solving the gradient. And by the delta method is very easy. We just express the random variable around the mean value using Taylor expansion, and you could see we replace the random variable W star with mu W star, which is the expectation from the first layer of the Gaussian process, and plus some and that's the residual from the Taylor expansion. And here the residual terms represents the high order uncertainties and becomes negligible if the variance of the W star is relatively small. Yeah, and in our task, we targeted at interpolation. So the variance, there is no such kind of variance we need to consider from the function itself. So the variance of the W star will decrease rapidly as the amount of training samples increases in our cases. So finally, the the covariance of the gradient of the global of the variables can be expressed in this way. We iterate the PGP emulators in the first layer and compute the gradient contributions of each first layer sub GP and sum them together. Yeah, and there are definitely some trade-offs to compute the covariance here. The drawbacks here is the delta method simply the good side is this kind of method simplifies computation. But the drawbacks here is that we assume there are very small variance in the W star. So using this method, we definitely lose some uncertainties consideration. Lose some kind of that's the drawbacks of this approach. And a more systematic and accurate approach to quantify the uncertainty maybe involves Monte Carlo sampling from W star from the first layer of GP and then take the gradient because we can solve it for the GP case and then propagate through the second layer. But this is very computational expensive. Yeah, and as we do for the DG from the linked GP to deep GP before, we also compute the ensembles of the each linked GP, imputed linked GP to form the approximation of the DGP gradients posterior distribution. Yeah, and here we did some numerical validation of our derivations in a very simple test example with the fx equals some sign function, and it's a partial derivative given by the second equation. And we evaluate the accuracy with respect to the normalized root mean square error defined in this way. Yeah, and that's the result we obtained. So the left figure shows true function value, which represented by the color contours, and the red arrow represents the gradients at each test point. And the blue triangle represents the training samples. And yeah, in the second figure, is the result we obtained by a stationary Gaussian process. And you could see it's just it can performs very badly about the function value itself, and definitely the gradient is also very not in our expectation. And the uncertainty ellipse represented by the blue dashed curve. And you could say because the emulator lose performance, so the uncertainty quantification, the ellipse just reflects the isotropic property of the standard Gaussian process. And that's the figure C represents the result we obtained from a deep Gaussian process by the gradient computed in finite differencing, second order finite differencing, which means we select the 4 points in the 2D case around the test sample and do a second order finite differencing to compute the gradient, but it cannot quantify the uncertainties. And the right figure shows our results using our derivation. We can see that it's accurately captures the gradient value, and the uncertainty ellipse successfully captured the trend of the function because in that direction it's very stationary. There's no changes, so the uncertainty in that direction was very tiny. But in the diagonal direction, the function fluctuates very much, and the uncertainty will also be large and reflects in that direction. That's why you see it's not a cycle; it's a more flight ellipse here. Yeah, and there's some quantitative results we obtained by comparing some other gradient estimation approaches. The figure A shows the accuracy with respect to GP, finite differencing, and we also recoded the deep Gaussian process with some automatic differentiation framework. And here we're using the Python library JAX to redo that. Yeah, and because the AD also analytically compute the gradient, so the accuracy is exactly equal to us. And the B and C compare the computational time. The figure B shows how the computation time scales with the training samples because we know GP is a non-parametric approach with the increase of training samples, the inference time increases polynomially, and because the finite difference you need to evaluate it for each test point many times to get a good order of accuracy. So it very time consuming. And the green one is automatic differentiation implementation of the deep Gaussian process. And with a low number of training samples, the time most spent on computation, created the computational graph of the deep GP. And that's some issue, not issue, some process of the AD. But with the training sample increases, it becomes very efficient because most of the time spending in the inference rather than create the computational graph. Yeah, and the right curve shows our approaches. The solid curve without UQ and the dashed curve with UQ. Yeah, and it still lower than the AD approaches in low number of samples, but our scales exponentially with training samples, and we are thinking about how to handle this challenge in the future work. And the figure C shows the time, how the time scaling with the dimensions. And yeah, with the finite difference in the required samples increases exponentially with the dimensions, so you can see how it scales. And in this case, our approaches performs quite similar to the AD approach, even with the UQ. And the GP is a very simple emulator, so it's sufficiently fast. And here I want to introduce our well-developed code called DGP-SI, which is a comprehensive package for GP, DGP, and linked GP emulation in computer simulators and more challenging simulation tasks. And it supports both R and Python with some features. We support some online tasks like sequential design, Bayesian optimization, and some engineering design tasks. And it is scalable because we enable the multi-thread parallel implementation and the various low-rank approximation of the Gaussian process. And it's also enable very flexible likelihood. The DGP frameworks with like Bernoulli likelihood, which applied in classification tasks, the heterostatic case with modeling different noise level, and negative binomial and etc. And from this work, we also developed the gradient estimation of the DGP with uncertain quantification, and we are also thinking to apply these features in some downstream tasks like sensitivity analysis. And the documentation and the tutorials can be found in the following URL. The package now is developed by my colleague Deyu, and right now maintained by Deyu and myself. Yeah, quite a long story. And after introducing all the previous stuff, I need to introduce the concept of the sequential design. So what's mean by sequential design is like it's a loop to optimize a certain metric you're interested in. And during the loop, in each loop, we need to minimize certain thing to select the next next data points, and there are also other names like active learning, like Bayesian optimization in different communities. So very important concept about is the acquisition function G, which means the function you want to maximize to select the next data position to sequentially achieve your ultimate goal. And yeah, it used for many different purposes. Like I wanted to build a global approximation of the underlying functions, or I wanted doing the optimization to find the best parameters that optimize my metric. Well, yeah, as I firstly introduced before, what we are interested in about the localized sharp variation regions, and of the computer model F, which is I find a suitable definition called the weak discontinuities, defined by the region G, which each point in this region um, satisfy the first equation, and the L is a certain rate of changes of functions, and yeah, in a very standard way, you can say that L is the Lipschitz constant, and if we beyond this kind of thing, kind of rate, uh, so the changes will quite differently from other regions. Yeah, and from this definition, our target right now is identify these high variation regions and build efficient emulators. So we recast the region D as a super level set of the gradient of the norm of the gradient. And this is an example. The left figure shows the 1D case, where the right regions shows the weakly discontinuous region D, and the middle one and the right one are the 2D case. Uh, and the right one is a 3D contour of the middle one. So our key idea is like treat identifying D as a level set estimation problem on rather than on the functions, but it's on the norm of the gradient. So because in Euro level set estimation problem, they targeted the level set of the function value itself, and which the purpose different align with ours here. So I think about the probability about the gradient norm beyond a certain threshold, which if we recall the definition of the region D, which the probability of the point X belongs to the region D. And there are the very well-known entropy-based criteria to sample the next design point X. By in this way, intuitively, we treat this variable as a binary variable, and that's the likelihood of the Bernoulli. And we all know that the entropy will be maximized as a 0.5, which is a boundary of the region D. So the challenge here is how could we evaluate the probability Px, and could we get any distribution for the gradient norm? And the answer is yes. So let's consider like the posterior distribution of the gradient expressed in a normal distribution. Uh, and the covariance matrices here we consider is the diagonal one. So it's uncorrelated between each dimension of the input. And given threshold, given a certain threshold, the probability can be evaluated in this way: 1 minus f chi f chi function, where the chi is the non-central chi distribution, and the non-central, how we shift from the central one is defined by two things. One is the degree of freedom, which is the dimension of the problem D, and the non-central negative parameters, which defined shown in the lambda chi, and yeah, and the idea of this result was very intuitive because the sum of square of the gradient, if each component of the in the gradient follows a normal distribution, the sum of them is a cos square. But you're non-central, so that's called non-central cos square. And when you take a square root, it follows the non-central cos distribution. Yeah, and during the sampling, we have some practical consideration. If the threshold L is unknown, and we find a way to iteratively update the L from by treating the maximum gradient norm within the rest the unexplored region of our domain. Yeah, because of time limit, I wanted to accelerate it. And there is another issue of the over concentration because if the function itself is a truly discontinuities and your emulator or approximator will capture that and it will cause very large gradient values leading to you only want to samples around that point and do not explore. So our solutions is using a bi-objective Pareto frontier framework to balance our acquisition function and also the uncertainty about the regions which give us from our DGP emulator. And that's the concept of the Pareto frontier, which is defined in this way. And the symbol here is means dominant. So what I mean by that is the for the points not in the Pareto frontier, it means you cannot simultaneously improve the two objectives, and we call all the points in the Pareto frontier called the dominant. The rest of the points. Yeah, and we finally the numerical result of our sequential design, and we compare with some very famous uh, sampling approaches. We are first three ALM, MX, NICE, and VGF, and with Gaussian process emulator, and we also compare with deep GP emulator approaches. And we think of two metrics. One is the global approximation error, and another is the local approximation error. Yeah, and that's a result in the 2D synthetic test function. And we can see the global and the local error. The x-axis of the figure A and B are the number of samples, and the y is the approximation error. And we can see like for both global and local error, our approaches decay very fast and achieve a very nice result with tiny uncertainties at the end. And the figure C shows our estimated probability px, which defined by this guy. You can think of the probability um, of the point belongs to the sharp region D. Yeah, and the dashed black curve shows the true transition area, true variation, high variation region. And there's some realization of the sample locations during the sampling, and the different colors indicates the sample iterations. And for the first two guys, because they are uncertainty dependent metrics, they want to minimize uncertainty, so they put lots of points around the boundaries and not effectively explore the true region we're interested in. But for the VIGF, it captures the variation, but put too much points and too much points along the variation and happen some concentration behavior. And that also happens for the ALC DGP. And with our practical consideration about the Pareto frontier, it balanced the exploration and proliferation to better cover the whole domain and put more points along the region we're interested in. And that's for some performance in high dimension with dimension 5 and 8. Yeah, and we consider a more realistic example in the fluid dynamics. The Lorentz theory, which is a simplified model for heat convection, which defines the nonlinear ODEs, and the stationary value of the Z, the component Z approaches the Newton number, which measures the heat transfer conductive efficiency. So we think of the nu as a certain function with input parameters sigma and rho. And the function f here is a long-term integration of this ODE because we care about the stationary Z. And in physics, the two terms represent the two dimensionless numbers of the heat convection system. Yeah, and the figure A shows the transition behavior. And if you see like beyond within the sorry after the sharp transitions, the system becomes chaos, which is a very famous butterfly shape of the Lorentz three. But when you the upper level, it shows a fixed point, and that shows a very stationary behavior of the system, and that's corresponding to the laminar heat transition and the turbulence heat transition phenomena in the system. And the figure B and C shows the challenges of this problem, which is a cross section along the 2D surface. So the first thing is the jump magnitude is different. So it may be more easier to capture the black curve is a higher jump and ignore the orange one because it shows a more small jump. And the C shows there is a rapid rebound. You can see like the black curve here. It's very hard to exactly sample along this very tiny valley here. If you sample here, it just ignores the non-stationary behavior. And this is the result of the Lorentz three problem. And yeah, as before, the A and B are the global and the local error of our method against the number of design samples. And you can see our method quickly decay from the 50 samples and much better than with much smaller uncertainty compared with the ALC DGP method. And again, the figure C shows our estimated probability that the point X belongs to the high variation region D. And I'm very satisfied about the result because the geometry of the transition curve now much complicated, which indicated by the dashed black curve. Yeah, and again, that's some realization of the design locations generated by different sequential design algorithms. Yeah, and as before, the ALM math GP-based method uh, allocate much more samples along the boundary, and for the VIGF, it's stacked in certain locations and stop exploration of the whole region. And ALC DGP performs reasonable well, but it still happens some concentration issues. Where in our method, uh, it will capture the triangle regions, which most tricky part. Yeah, and that's all. Thank you very much for your attention. Uh, uh, could you hear me? The online friend. Uh, right. Okay. Hello.